So matter is one of the categories of all things. Anything that does not fall into the category of matter, meaning it has mass or takes up space, generally falls into the category of energy. Okay? So in general, we define energy as the ability to do work. Okay? Energy is the ability to do work. Okay? Now, that doesn't mean that it has to be hard work or work where you're actually expending energy. Most people think, okay, well, work involves me having to lift or move some kind of object or build something or create motion of some kind. Not necessarily. When you turn a light bulb on, that light bulb is not then doing work. Okay? It is causing something to happen or producing something. In that case, it would be light. Okay? So, the ability to do work. It is everywhere, all around us, and it makes things happen all the time. All right? There are 5 forms of energy. All right? Repeat after me. Light energy. Mechanical energy. Sound energy. Thermal energy. And electrical energy. Good. Okay? All right, now let me briefly describe these, and then we're going to get into light energy. Light energy is obviously all forms of light. Okay? Now, some of them you can see with your eyes, some of them you can't. So we're going to talk about today just a little bit. Next, we have mechanical energy. Okay? Mechanical energy is the energy of motion. Either the potential to move or the kinetic action of actually moving. Okay? Potential is usually when something is like a roller coaster at the top of the hill. It's about to fall down the hill. It's in a position where it's about to have a lot of motion. Does that make sense? Kinetic energy is when it's actually moving. But we'll talk more about those later. Sound energy is a particular energy created by when you rub 2 objects together. In the case of your voice, it's your vocal cords rubbing together. Okay? Creating the sound of my voice. Next one is thermal or heat energy. Okay? The more energy that the object has, the higher the temperature. Okay? The less energy it has, the lower the temperature. We'll talk more about that later as well. And then electrical energy. Most of you are probably familiar with electrical energy, but we're going to discuss it a little more in detail. I think tomorrow is electrical energy. So, light energy. All right? The rest of today, we're going to focus on one kind of energy, specifically light energy. Light energy is energy carried by light and other forms of electromagnetic waves that we cannot see. All right? Light energy actually includes the entire, what we call electromagnetic spectrum. Okay? This is all the different size waves of energy that travel outward from the sun. All right? The sun is our main source of light energy. Okay? Now, yes, you can turn light bulbs on. That is actually light produced by electricity. Okay? Different kind of light. Light energy from the sun actually emits all different size waves of what we call radiation. Okay? If we could see them, you would see little waves traveling from the sun all over the place. Okay? Now, based on how big or small those waves are, you have a different kind of radiation. Okay? Do you see how these waves are further apart than these waves? Okay? That's called the wavelength. All right? These have a very long wavelength, and as you go across the spectrum, they get to shorter and shorter wavelengths. You see? It kind of goes like this. Long wavelengths, nice and spread out, shorter, a little shorter, and really short. You see what I'm saying? Okay. So, all the waves that come out from the sun could be anywhere in this spectrum. All right? If the wavelength is the longest kind, okay, so it's about 10 to the second power nanometers, 10 to the negative 1 power, fancy words for saying the length, okay? This is radio waves. This is the longest wavelength of radiation from the sun, okay? Now, that is just like it sounds. Radio waves are how we transmit radio signals, like what you pick up in your car or walkie-talkies, things like that, okay? Get a little bit shorter, these are microwaves, all right? Which a microwave oven, like what you heat up your Hot Pocket in, okay, when you put that into the microwave and turn it on, the machine actually emits waves of radiation that are this length. Those waves travel through the food, and at that motion causes it to heat up. Okay, that's how a microwave works. A little bit shorter than that, you get infrared radiation. Okay, this is if you've ever watched like a spy movie, or if you ever use an infrared radar on a gun, this usually is it senses heat energy, heat sources. Okay, you can't see it either, but when you use the right machine, it can help you see different heat levels. Okay, now get a little bit shorter. This tiny little section right here. This is pretty amazing. This tiny little section. Stop waving your hand around. I will get to you when I have a minute. This tiny little section right here, this is visible light. Okay? This little itty bitty part is the only part that we can see with our eyeballs. Our eyeballs are only structured to be able to see and sense these wavelengths. Okay? I'll get more to that in a minute. Get a little bit shorter, you have ultraviolet light. Okay? These are the rays from the sun that will give you a sunburn. Okay? When you put sunscreen on and it gives you UVA or UVB protection, or your sunglasses have UVA, UVB protection, that is blocking these particular ultraviolet rays from the sun. Okay? Get a little bit shorter and you have X-rays. Okay? X-rays are a little more powerful. They can travel through your skin, but not through your bone. Okay? If you go to the doctor and get an X-ray, can you see the rays coming from the machine? No. They're too short. They're out of the visible light spectrum, right? But they can travel through your skin, but they cannot travel through your bone. Okay? Which is why it basically creates a shadow of your bones onto the paper, so you can see, do I have a break in there anywhere? You see what I'm saying? Okay? That's an X-ray. And then the shortest wavelength is a gamma ray. Okay? I'm not super familiar with gamma rays. They are extremely powerful, but I believe these are the kinds used for cancer treatment, radiation treatment for a cancer patient. Okay? They can actually target that kind of radiation right on the spot where the tumor is or where the cancer is and try to kill the cancer cells. Okay? Now, too much radiation can kill you or make you sick. Okay? Kind of like nuclear radiation or things like that. Okay? Also, if you're into comic books, I believe this is the kind of radiation that made the Hulk. Okay? So, anyway, they are a real thing, but they won't make you into the Hulk. Sorry. So, this is the entire spectrum of waves that come from the sun. Now, if we zoom in on just this little part, just the little part that we can see with our eyes, that our eyes are trained to see, the different wavelengths within that little part create the different colors. Okay? So, this NM right here stands for nanometers. Okay? Nanometers. The longest wavelength that we can see is 700 nanometers. All right? That will let you see the color red. A little bit shorter, maybe 650 or something, you see the color orange. Around 600, you see yellow. A little shorter, you see green. A little shorter, you see blue, light blue. Then you see dark blue. Then you see violet. Anything shorter than 400, whatever this is, 370 something, I don't know. Shorter than this nanometer length, you can no longer see it. It then falls into the ultraviolet section. Does that make sense? Okay. So, before I take your questions, I think the next part is writing the order of the colors. Oh, no, okay. The shortest wavelength, we're going to fill in the notes. I'm going to explain a little more, and then I will take your questions, so just hang on. Okay? The shortest wavelength is violet. You can't see it very well, but it says violet. The shortest wavelength is violet. Anything shorter than that, you can't see it. The longest wavelength is red. Anything longer than that, you can't see it. Okay? At the bottom of that page, it says, what is the order of visible light from longest wavelength to shortest? Okay? It's the exact same as the order of colors in the rainbow. Okay? Gavin, put your feet under your desk and face this way. So, the trick to remember the order is Roy G. Biv. Raise your hand if you heard that before. Good. Okay. So, in your notes, you're going to write it just like I'm writing it here. Roy G, oh, we're out of space, Viv. Okay? Underneath those letters, you're then going to write the color. So this is going to be red, orange, yellow, green, blue, indigo, and violet. You do have to know the order of the visible light spectrum for your test, I believe. Okay? Roy G. Bibb. Red, orange, yellow, green, blue, indigo, violet. Red is the longest. Violet is the shortest. Okay? Nicholas, quick question. Mm-hmm. So what? The channel? No. Mm-hmm. Interesting. It's really cool. That is cool. Check it out. Interesting. That is interesting. Never heard that. Trinity? Yes. I mean all of it. Now, when you're seeing the light, like white light produced from a light bulb, that's actually a combination of all these colors together. Okay? When you see that is combination with, okay. So what I mean by that is if we were in a dark room and with all the only radiation that was being sent from, like, the only wave that was being sent to the room was ultraviolet light, we wouldn't be able to see anything. Does that make sense? If the only waves being sent through the room were microwaves, we wouldn't be able to see anything. But if the waves being sent through the room were somewhere in this spectrum, we would be able to see it. Does that make sense? Okay, so here's the thing with black, and really all colors. When you see colors, you're not actually seeing, well, so okay, when you see blue on my cup here, okay, the light that's hitting my cup, the cup is a solid object that absorbs all of the light rays except for blue. Blue is reflected back to your eye, which is why you see blue. Okay? Let's see. My red marker here, the red cap. Okay? This object is a solid object, absorbing all of the light rays except for red. Red is bouncing back to your eye, so you see red. Black, that object is absorbing all the colors. White, that object is bouncing back all the colors. Does that make sense? That's why when you wear a black shirt on a hot day, you get hotter. But you wear a white shirt, you feel cooler. That's why. Okay? Good question. All right, I'll do 2 more, and then we got to move on, or we won't. Maybe 3 more, depending on time. Caleb? What about for gray and pink? For green and pink? Gray or pink. I'm not 100% sure, because I'm not like a light chemist or anything, but my assumption is that for pink, okay, there is some white light being reflected back and some red light, which is mixing and causing you to see pink. That's what I think. I don't know that for sure. I could be totally wrong. Yes. So I don't know if this is light or if it's connected to something with heat, but when it's a really hot, and then you can see some of the rays from like really hot. Mhm. Okay. I don't know 100% what that is. It is either the movement of the light rays, or it's a vapor, like steam or evaporation or fumes or something that's causing the light to kind of bend a little bit, which is letting you see the wave. I don't know for sure though. Okay, Davin, Sophie, Bella. We're gonna move on. Davin. Did you know magenta is technically an impossible color? How so? I mean, Can you explain them? Okay.
There's also like colors.
Interesting. Sophie? That's a good question. So, sight, what you see, has everything to do with the nerves in your eye. Okay? So, in your eye, you have your retina. That's like your big nerve in the back of your eye. And within the retina, there are rods and cones. 2 different nerves. Okay? For someone who is colorblind, it's not that they can't see color. They just mix up some of the colors. So, either the nerves in their eyes don't work properly, or the communication from their eye to their brain gets messed up. So it kind of like it kind of flips some things. Instead of your eye saying, "Oh, it's blue," it tells your brain that's red or whatever it is. Does that make sense? So color blindness, the object is still doing the exact same thing as does everybody else. It's the eye that's either interpreting it right or interpreting it wrong. Does that make sense? Okay, Bella.
So you said it's the lighter
Mm-hmm.
Then what happens in the dark? Maybe not the specific term because of the window, but like you're in a bathroom and it has no window.
Mm-hmm.
And you turn off all the lights around it, and there's no light coming in whichever way. So how would you still see color?
You wouldn't.
Unless you put something really close to it.
If you're in a completely dark room and you can't there is no light whatsoever, you won't be able to see anything. If you're in a dark room but you can see a little bit, like you can see, but it's not like super bright. You can just your eyes kind of adjust. You can kind of make things out. You know what I'm talking about? That means there is some presence of light, just not a lot. If it's completely pitch black, no matter what you do, you will not be able to see anything. Does that make sense? Okay. Moving on. How does light travel? Okay. Light starts with a vibrating charge like an electron. Okay. In order for light to be produced, the electrons of the atoms get heated up and begin to kind of move around. Okay. When those electrons vibrate and shake, it's just like when you kind of shake or vibrate or jump up and down in a pool. What happens when you bounce up and down continually in a pool? You create a wave pool, right? If you're in a hot tub or even in your bathtub, if you bounce up and down, you're going to create waves, correct? Same thing happens with an electron. If an electron is activated, so to speak, to where it vibrates and moves around, it will start to create waves. Depending on the wavelength, it will either be microwaves, infrared waves, visible light, etc. Okay? So it starts with a vibrating electron creating the waves. How fast or slow the wave moves depends on the source of vibration. If the electron moves slowly, you might get that long wavelength, like a microwave. If it's going around crazy like this, you might get a gamma ray, super short wavelength. You see what I'm saying? Depends on how fast the electron is vibrating. Light also travels at very high speeds. The speed of light, I do want you to write both of them that you see on there. Okay? The speed of light is 299,792 kilometers. But we're not super familiar with kilometers. So, per second. Sorry, per second. But in miles, that's 186,282 miles per second. Ouch. Okay? So, 299,792 kilometers per second or 186,282 miles per second. You got to write both of them in your notes. Okay? Now, let me put that into perspective for you a little bit. In your car, the fastest you drive on the highway is maybe around 90 miles an hour. Okay? 90 miles an hour is not even 1.5 miles per minute. Okay? Which means every second, you're not even traveling 1 mile. Okay? Light, 186,282 miles per second. Okay? It is the fastest speed that we know of. If you're a Star Wars fan, when they talk about jumping to light speed or warp light speed, that is what they're talking about. Now, we can't actually send objects that fast, at least not today. Okay? Light is the only thing we know of that can travel that fast. This is also why, if you've ever been to like a fireworks show or something, and you can see the fireworks sometimes before you hear them, if you're really far away, okay? Because the light travels faster than the sound. You can see it before you can hear it. Okay? Nicholas. Yeah, there's a lot of theory around that, yeah. Okay, so to put it in perspective, the sun is almost 93 million miles from the Earth. Okay? Here's what I want you to do. Think about the biggest place you've ever been to. The Grand Canyon, the Palo Duro Canyon, if you've ever been on a lighthouse and looked out, if you've been on a really tall building, maybe you were in a hotel room, looked out and saw a really big area, right? Think about the biggest place you've ever seen. Okay? Now, think about that view. You're only seeing that city that you're in. Okay? That isn't a city. Okay? You're only seeing that city that you're in, or wherever that thing is located. That city is a one tiny spot within that one state. That one state is one tiny state within the one country, within the one continent, within the one Earth. Okay? The Earth, then, is a massive, massive place, correct? Okay. The Earth and the Sun is a distance, right? Between the Earth and the Sun, we could fit every single planet in our solar system and still have tons and tons of space. Okay? The Sun is way, 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 way far away. Okay? At the speed of light, it takes 8 minutes for light to travel from the Sun to the Earth. Okay? When you step outside, the light that hits your skin left the sun 8 minutes ago. It's crazy to think about. If you step outside at night, the light that reflects from the moon left the surface of the moon 1.3 seconds ago. Now, the moon does not create light, it only reflects the light from the sun. But still, at the speed of light, it bounced off the moon 1.3 seconds ago. And is now hitting you. That's crazy. Okay?
That's only because the sun is always giving off light, so it doesn't seem like it takes 8 minutes because it's always
just doing it over and over again. All right. Now, there are 4 things that light can do when it hits a piece of matter. Every light wave, whether it's visible light or gamma radiation or whatever, every ray will behave in one of 4 ways. The first thing it can do is transmit. Okay? Transmit is when you have the object and the light ray goes whoop, right through it. Okay? A window, glass, transparent object, clear object. Light transmits right through it. Okay? The next thing light can do is reflection. Okay? Reflection is when light hits the object and bounces right back where it came from. Okay? Reflection on a water surface or a glass surface or a mirror. Okay? Any of those. Refraction is kind of funny. Refraction is when light passes from one medium to another, for example, from air into water, and it changes or bends or changes direction slightly. Okay? So look up here. This is transmit. Look up here. Transmit, it goes right through. This is reflect. Boink. This is refract. It comes through, changes direction, and keeps going. Okay? It actually bends the light. Have you ever been in a pool and stuck your arm under the water and looked at your hand?
Yeah.
It looks funny, right? It looks like your arm's broken and your hand's sticking out in a weird direction. That's because the light traveling through the water and then into your eye changes direction before it gets to you, which is why your arm looks funny. Okay? And the last thing you do is be absorbed, meaning it gets taken into the matter and stops, ceases to exist. Okay? So, this is transmit, right? Light hits the object and goes right through it. Okay? This is reflect. The light bouncing off from here is hitting the water and bouncing straight to your eye. You're seeing a reflection of the object. This is refraction. Okay? It looks like the straw is broken, but it's really not. The only thing happening is the light waves traveling from here to your eye, so you can see the straw down here. Okay? It's bending once it comes out of the water and into the air, making it look like it's broken, but it's not. This is absorbed. Okay? When light hits a solid object, and the object absorbs the light. It's not reflecting, it's not refracting, it's not transmitting. It's actually even creating a shadow behind it. Okay? That would be when it's absorbed. Okay. All right. Now, question for you. What do we normally use to see a reflection? Class?
A mirror.
A mirror. Good. Now, we just said that a mirror works by reflecting all of the light. But I also told you that white objects reflect all of the light. Now, if both of those are true, why can I see my reflection in a mirror, but I can't see my reflection on a white piece of paper? What's the difference? Landon? The mirror? No, it doesn't absorb it. They both do reflect it. Well, if it was clear, it would go right through it. I'm purposefully asking difficult questions.
I know.
Sophie, what do you think?
Shiny. Because if you think about it, a lot of very shiny things.
Okay.
It's not wrong.
But what allows you to see the reflection is the light rays bouncing off the shiny thing and back to your eyes, right? But I'm telling you that a white object does the same thing. It bounces back all colors of light back into my eyeball. So what's the difference? Reagan?
I think it's because the certain amount of light that's going through the certain substance of how it reflects the light and the way it kind of reflects it.
Okay.
And this, when you look at a white thing, it reflects the light, it bounces back into your eye. The thing that you see in the mirror is the type of substance or the type of material and the way light bounces into it.
You're kind of on the right track. Okay, let me explain. The difference is the surface characteristics of the two objects.
That's what I was
Okay? The smooth surface of the mirror reflects the light, much like bouncing a tennis ball on a tennis court. If I bounce a ball on a smooth, flat surface, what's going to happen? It'll bounce right back. But what if I bounce the ball on a rough, bumpy surface? It's going to go all kinds of directions, right? It'd be like dropping a ball into the Grand Canyon. It's going to bounce all over the place. Okay? When light hits the white paper, it's like the Grand Canyon. If you were to look at paper on like a molecular or under a microscope, you would see that paper is actually a bunch of fibers all woven together. It's not perfectly smooth. So when the light bounces back, yes, it all bounces back, but in all sorts of different directions. Not all into your eye at one time. Don't talk. A mirror that reflects light like a tennis ball on a tennis court. The light hits it and comes right back in the exact same direction. When all of the light does that at one time, that's why I can see the image. You see what I'm saying? Paper reflects it back in all sorts of directions. So I cannot see what's being projected onto the paper. Okay? Mirror bounces it back all nice and smooth in the exact same direction it came from. in your notes, hold on. Here's what you're going to write. Here's how I want you to say that. Well, I mean, this one right here. The smooth surface of the mirror reflects the light back where it came from. But the paper reflects the light back in all sorts of random directions. Reflects. The smooth surface of the mirror reflects the light back where it came from. But the paper reflects the light back in all sorts of random directions. Ethan A? Correct. That has that has to do with what we're talking about next, which is lenses. When an object is reflective but it's curved like that, it kind of plays around with the light rays and they're not bounced back the same way. You'll see. Maybe, hopefully. Okay? Kayla?
What color is the mirror?
What color is it?
Yeah.
I don't know that it has a color. Interesting. I have to look it up. I don't know.
Every color.
Hush. Hush. All right.
What's that word say?
All sorts of random directions. From. Where it came from. Reflects back where it came from, comma.
Oh.
But the paper reflects the light back in all sorts of random directions. Connor, you can go for a warning or you can wait about 10 more minutes. It's up to you. Nicholas?
Or you can also compare the ball and dropping yourself.
I don't think so.
But we can like dropping a rock down the Grand Canyon or a tennis ball down the Grand Canyon.
Except for the tennis ball will bounce back.
Yeah.
That's the point.
Or the rock would just the rock would just drop and not go back on.
That would be like absorbing, I guess. All right. No. Shh. Shh. All right, moving on. So we have time to finish and give you the homework. White light. White light is visible light coming from the sun, and it is also the light that comes from light bulbs. It is a mixture of all the colors shining together. Now, just like we learned with Isaac Newton, a prism, a triangular prism, is a tool that helps us to observe white light. When the white light hits the prism, it actually splits it into all the colors of the spectrum. Okay? Proving that the white beam before it was split up is all of these combined. That was what Isaac Newton proved. Okay? Now, the other tool that we can use to help us observe light is a lens. Okay? A lens is an object used to refract or bend the light. Okay? There are two kinds of lenses. A concave lens gets skinnier in the center, but thicker on the outside. Okay? I think of it like this. The lenses curve inwards like a cave in a mountain. Concave. Okay? When light hits the concave object, the light rays actually spread apart. Okay? So it goes like this. When a light ray hits the concave lens, it actually splits. Okay? So what looked to be this big on this side is this big on this side because it spreads the rays apart. Okay? So a concave lens magnifies the object. Okay? A convex lens does the opposite. It actually focuses the light. Okay? The light rays are all hitting the concave lens, and it causes them to converge, is what it's called. They all come together at one point. So this does the opposite. The object that is this big on this side is now this big on this side. Okay? Because it can help focus the object. Okay? Now, this is exactly what happens if you've ever been to the eye doctor, or if you wear contacts or any kind of glasses or things like that. Okay? If you're nearsighted or farsighted, depending on the strength of that, your lenses are shaped a certain way to help your eye focus. Okay? Now, a great example. I have one nearsighted eye and one farsighted eye. Okay? So my lenses are opposite. So if I hold them up, do you see how one lens behaves one way and one behaves the other?
Wow. Wait, I can't snap.
Probably.
I know, right? No, we did it with the rainbow. You're lucky.
Okay? So, the different lenses bend and focus the light in different ways. Okay? All right. So that's the end of the notes for that, right? Oh, no. Did you guys draw the picture?
No, I'm doing that.
All right.
I did it.
For the concave lens, you're drawing the magnifying one that I have up there. So if this is the lens, the light hits it here and it actually spreads apart, making the object bigger as opposed to smaller. Let me erase this. Okay. That's the concave lens, curving inwards like a cave. Okay. The convex lens, the light hits it this way, and it all converges, comes together at a single point, making the object that was big look small. Okay? Reagan, question?
Yes. Whenever you're looking at like a window, sometimes it's